Hello everyone, I am Dr. Jai Singh, coordinator of CE 201 C subject and mechanics of materials, and this is another video lecture of CE 201 C, and this will cover build up beam section. It is a continuation of previous video lecture. And here, what is build up section? The build-up section is we are using, I will explain in this manner simply. So we are using different parts, and think about, we have these kind of plates, and by using this plate, interior plate, by assemble, we can develop the section. We can assemble the section like this. So of course currently it has like a 3 plate. Now we are assemble to get like a build up I section. When you come to the build up section, of course it's like not like a previous case. In previous case I sections, actually it is steel or any other, it can be any material, but these are cast one shot. There are no any such a connections or other things. We directly cast it and we use it. So these are not a build-up section in the previous section. In here we are going to focus about build-up section. Build-up section is we have like a different parts, and the part, more than one part, we going to assemble to get the relative or directly or the beam sections. When you come to the build-up section, we can categorize this build-up section to mainly 2 categories. So we'll see this one. When you come to the build-up section, now you already know. In the build-up section, we can category under 2 categories. One is we call the compound section, other one called the composite section. Compound section, here we can see directly as a steel I section, the timber assembly structure. And here we are using same type material, no different material. Okay, that means if you're talking about build up section, and under build up section, if you come to the compound section, we are using same type material, no difference. You can see this is also assemble of parts. We have like a different part we are assembling by using bolt connection, and here we are using nail connection, and we are assemble and we are using. And when you come to the composite one, of course here again these are different part we are assembling, but we have different materials, different part of beam section in different materials. As example, here we can see sandwich structure. So we can see here timber, and inside that one we have steel plates, and here we can see concrete. Inside concrete we can see steel I section. So the difference is come in here we are using same material, and here we have different more than one type material. So the definition of build up section you are clear now. So we have different parts and we are assembling and we are building up our relevant sections. When you come to the composite, you can see we are using same material. So that means there are no problem of using our simple bending formula to find the normal stress, simple shear formula to find the shear stress variation, because if you can remember, when you're going to derive this equation, there are main 2 measures. One is like a linear, it should be in the linear range, and other one should be the homogeneous material. So this is a homogeneous actually. Only thing we need to focus about the disconnection part. Of course we are using different same material, but part we are assembling through bolt or nail or some kind of connector. So if connector can transfer shear stress, so bending is stress efficiently. So then this unit going to work as one part. Okay, then there are no trouble of using this equation. Okay, we can use simple bending formula. If you can remember simple bending formula, sigma to find. So it is something like this: M I sigma over Y E R. Okay, so here you can see the simple bending formula without trouble. Or shear, so it is again shear stress is Q time IT. Okay, so these equation without trouble if we have a good connector. So with good connection within each layer, good connect 100% good connection. So then without trouble we can use it. That means like we are not expecting any sliding between those layers. Then if we have zero sliding, we don't need to worry, so we can use it. So I will remove these things. Now think about composite section. So how about composite section? Can we use this simple equation or not? That's the question. So when you come to the composite section, so I will remove these things. Okay. So when you come to the composite section, yes, you have a trouble of using this simple equation: sigma or M I Y, because of this is not the same material and we have like a different material type. So if we have like a homogeneous and same material, so no trouble, we can use it, but in here there's a trouble to use it. And here we will see how we going to modify these equations to fit this kind of condition. In here you are clear, we are working with like a linear range analysis. When you come to the linear range, mainly linear material property. They have three type main linear material properties. So these are E, nu and G. Okay, so you know, and from previous or very first lectures, if you know two things, you can predict the other one. So we can remove this one, then only these. And again in here we are not interested about Poisson effect, so you can remove that one. Then as a material property we need to worry about this Young's modulus of these materials. So in this lecture, the first we're going to discuss about compound section. Now you know in the compound section there are no trouble to use this equation, we can use it. Only thing we need to worry about the connectivity or connection between each layer. So if we can provide 100% good connection, so we don't need to worry at all, so we can use it this equation. When you come to the composite section, we realize of course we cannot use directly these equations, and we need to modify. When you come to the modify, of course we are thinking about like a linear range, then the material wise we need to modify this Young's modulus. Okay, so these are the two things mainly we are going to discuss in this lecture. Okay, so now we can jump to composite section. So when you come to the composite, I already explained to act as one section. So act as one section, shear stress need to transfer from layer to another layer. So think about these two arrangement. So this is with shear connector, without shear connector, and this is with shear connector. So think about like some kind of glue or some things we have between these layers to prevent relative sliding. If we have such a connection between those layers, then that section or that system going to work as one unit. That means This section there are no any sliding, so work as a one unit. So actually if we can go to any cross section between this one, these are like a homogeneous materials, so without trouble we can use it. Now you realize again the most important thing is the connection between the layers. So the connection between each layer more important for this task. Connection, it can be nails, bolt or weldings or a glue type connector. If the layers are connected together, we can see then the longitudinal shear. You now know what is a longitudinal and transversal shear. Mainly we need to discuss about longitudinal, and if you know the longitudinal, you can predict the transversal shear. So that is previous lecture, okay. And acting between the layers will prevent the relative sliding. So then if we have good connection, so it will going to work as single unit. If you going to work as single unit, there are no trouble of using our simple equation like simple bending formula and simple shear formula. So mainly now we are going to work as about this connection type. So if you have nails, so how you going to design this one? If you have a welding connection, how you going to design this one? If you have like glue section, how you going to design? So if we have a good connection, no trouble. So now we're going to focus about the connection types. When you come to the here, so I'm going to directly with examples. So we are here going to talk about three type connection. First one is nails or bolts. Both we can use it, but here I'm using nails. Okay. So think about our example like this. So this is wooden section. We have a 4-part, 1, 2, 3, 4, and we have here we can see we are using nails to connect these. This is web, you know now, sorry, this is flange, you know this one, flange, and this is web, and this is web of this structure. So now you can see we are using connect flange to connect web and flange nail as a connector. So what is the purpose of this nails? The shear stress or shear flow of this flange used to transfer efficiently to this web. Okay, so that is a function of these nails. So here also same, need to transfer efficiently this layer to this layer. So this is a cross section of this structure or this build up section, and when you come to plane view, you can see this type of arrangement. Yes, of course, when you work with these type of things, we need to work with three main parameters. The first one is space between nails. Okay. Other one is nail strength. Okay. Nail strength. Other one is number of nails. Here you can see 2 nails we are using, or you can use more than that nails. So now what we need to do, we need to calculate shear flow or shear stress at that level, this level, okay, this level, and we need to check this arrangement is adequate or not for transfer this shear stress from web to flange. So flange to web. Okay. So when you come to here, you know this one, you can calculate this is a symmetric system. So directly you can find neutral axis without trouble. If you know the neutral axis, so it is straightforward to find it in A. So you can see here, and this should be in A. In here, of course, you can use a parallel access theorem, and you can find the bigger rectangle I about this axis and small rectangle about this one, and you can remove it. So or any other way you can do it. Okay, and if you know this one, so you just need to use shear flow equation. So you can find the shear stress or shear flow, both are fine, but here I am going with shear flow. What is the equation for shear flow? Shear flow is equal tau time B. Tau, what is tau means? Tau time B means shear force into Q first moment over I. Okay, this is a shear stress, shear flow equation. So in here you can see apply shear force at that cross section is given 10 kilonewton. Careful about unit. 10 kilonewton, I am using Newton here. So this is I, and I am targeting top layer, this layer. Okay, this layer. Okay, this layer. So area 20 times 200, that's correct. And this is a length here to this mid, 150 times 10, 150 plus 10. So you will end up with shear flow is 20.7. Shear flow means, you know, shear force per unit length to transfer to planche. Okay, so per unit length how much shear force need to transfer. Now we know in the shear strength of nails, normally given is this formula is like a Newton is a force. So we have like a two line of nails, so that means this nail you need to calculate two line. So how much shear force going to transfer, so you can calculate it, and you need to check it with spacing. I already explained. So in here we can work with three parameters. One is spacing, other one is nail shear strength, other one we can call the number of nails. So we can jump to here. So this is shear flow. So it is spacing. Here we need to assume, we need to find minimum spacing, because now we already know the strength and number of nails. So only parameter we can change D. And so in here the nail can two nails, and one nail has 1000 Newton, so it gives 2000 going to transfer through this space. And for this one we need to find the D. That means in the unit length it's going to transfer Q to D length. How much is, you can multiply and find it, and from this way you can easily find the minimum. This is a minimum spacing. So that means you can use less than that value, any value between 0 to 92.2. And again I'm telling, in this kind of arrangement, the connection with nail, so you need to play with three things. First one about like a D, minimum spacing. Other one is like a number of nails. Here we are using 2. The other one is strength of nail, and here we are using 1000. Okay, very simple calculation. And this is a nail type. If we going to work with like adhesive glue, so same structure I'm using. I'm not going to calculate again. I know how much going to transfer here to here. Shear flow or shear stress is a 21.7 Newton per millimeter, and glue strength normally given as this parameter, like an area parameter. So in here we have like a two line of glues. So here I need to find the glue strength. Okay, so if you think about like a glue strength, is F time, the unit is Newton millimeter squared. Now we know the amount that we need to transfer from this one to have good connection between this total shear without trouble, shear force, shear stress need to transfer through this layer. Layer means the glue layer. So simply you can calculate this one. So you need to convert this one to line force, this area force. To calculate line force, so you need to multiply by the connection length. Connection length is here 20, here 20. Connection length 40 into F, that is the per unit length, and it should be greater than or equal to Q, shear flow at that level. So that means simply you can find your glue should have the minimum strength to equal 0.54 Newton per millimeter squared. Okay, so that's a glue type. Thirdly, we can work with the welding. When you come to the welding, we have like a welding line. In here I am actually using two welding lines. So same shear flow is here, same shear flow, same structure I'm using, same cross section I'm using. So same shear flow is coming through this way, and it need to transfer efficiently through this weld line. When you come to the weld, again weld is directly given per Newton per meter. It's like a line force, line unit, line force actually. So Newton per millimeter. So we are using two lines. So that means it need to multiply 2. It should be greater than or equal to Q. So that means at least one weld line, there should be the strength of this value 10.85. So now very simple. Of course, you can work with like a bolt or revert to other connector, but very simple. When you come with like composite, mainly depend on the connector, because of the if you have like good connection, that unit going to work as together without sliding. If we're going to work together because of same material is there, so one type of material, without trouble we can use simple bending formula or simple shear formula. So to happen this one, that means we need to stop relative sliding. So to stop relative sliding, we are introducing connection between these layers. So in here we discuss three type of connection: nail, weld and glue type connections. Okay, so very simple compound sections. So it is straightforward to understand. Okay, so we can do very simple calculations and very example in tutorial number 5, and after that you can get more clear idea, or otherwise you can refer your textbooks or internet. You can get 1,000 of example for these kind of arrangements. Okay, now we will shift composite one. Here now already know, now we has a trouble to use simple bending formula or either simple shear formula, because of here we have different E material. It can be E1 or E2. Okay, so if you have like different materials, so we cannot consider, think about like this kind of arrangement, this kind of cross section. Think you have different materials. Okay, this is one type material and this is your second type material. So then directly simple bending formula or simple shear formula directly we cannot apply for this section. What here we are going to do, like we are going to convert this one type of material. Either you can convert to whole section to material number 1 or material number 2, or otherwise you can convert whole thing to another material like material type 3. Okay, and after that transferred section you can analyze by using simple bending or simple shear formula. So in here in this section we are going to focus, or we're going to discuss how we're going to do this transformation of the sections. Okay, composite section. Okay, so here, so we cannot apply simple bending formula for whole section directly because of the different materials, but we can use simple bending formula after converting the whole section to one type of material. As example, you can see this is very general section, and you can see there are two type of material type 1 and material type 2. Material type 1 we have E, and material type 2 as 2 we can see as E2. And here again I am explaining. So when you come to the linear, we are working with the linear material. So when you come to the linear stage material, we need to focus mainly three material parameters. But you already know, if you know two things, we can find other parameter, because of we have three material parameter, but any two work as independent, other one is dependent for other two material parameters. So we don't need to about G. And when you come to the E and nu in here, so we are not focusing about Poisson effect. So again we are removing this one. So only we going to work with the E. So that means simply what we are going to do, convert, transform it like we going to work with this E ratio. Okay. So in here again, so this is similar, so same way as a simple bending formulation. So here again we are assuming plane section remain plane. That's a very basic assumption, plane section plane remain. So if you cannot remember, please go to the previous handouts. And the other one is linear variation of strain. We are assuming this one, we are considering or we are thinking our section has compatibility because we are using two type of material. In this layer there should be have good compatibility, that means no slipping or no sliding. Okay, so if we have in such kind of assumption, such kind of arrangement, so we can simply use linear variation of strain condition. This is about compatibility of our section. So now we can start from this one. So we can generate equation. If we are assuming linear variation of strain considering compatibility of section, so you can write this equation. The y over r into 1 linear variation throughout the section. Okay. So based on that, we are going to start our formulation. So when you come to the here, this is very simple equation. This is concentration relation E epsilon. We can apply separately material number 1 and material number 2. This is met 1 and this is met 2. So directly we can apply, we can replace, we have a same strain. Okay, strain is same, ratio same way, we are going to change it, same strain, we are going to replace this one from this value and you will end up with this kind of arrangement. Okay, and the next what you're going to do, so of course we are expecting linear variation. Based on that we have this kind of arrangement. Okay, this kind of variation of strain across the beam, and when you come to the stress variation, you can see there's a difference. If we assume this kind of arrangement, E2 is greater than E1, then what actually using this simple equation, sigma, each layer we need to use sigma equal E epsilon. Here to here we have grade E, larger E, so because of that we have like a bit large slope, and after here it's going to jump directly to less slope and it's going to here because of E1 is lesser than E2. Okay, this is a stress variation. Of course strain there are no change because we are assuming linear variation considering section compatibility, and here we can see because of E is changing. Okay, now similar fashion as simple bending formulation. So we are first thinking in this system we can see only bending moment, there are no axial force. Because of that we can write this equilibrium equation. So stress into area, it gives the force F1, area 1 force, this is F2, area 2 force, it should be equal to 0. And now you know the values for these things, you can substitute and you can end up with this equation, and finally you will end up with this because R is not equal to 0. If R is 0 there are no bending, there is a bending, so because of that there should be R, so R cannot be 0. Because of that from this you can get it this equation. Okay, and same way, so you know section moment in here M, so now you know this is force and multiply by Y, neutral axis, from the neutral axis. Okay, this is we are talking from the neutral axis. I am not going to explain those things, this is a neutral axis, you can find the neutral axis. those things you already know now. So neutral axis. So here this is for section 1 A1, this is for A2, and it should be equal to section moment M. And after that again same way you can substitute sigma 1 and sigma 2, you will end up with this. And of course in here you cannot remove R because of this is M equal to M. And now we can recast equation 4, this one, and equation 5. Okay, recasting means we are going to use simple n. Simple n is where simple n is E2 divided by 1, that we call the modulus ratio. In here we know we are using E2 divided by E1, that means this ratio should be greater than 1 because E2 is greater than 1. Okay, you can decide anyway. In here actually I'm going to convert whole section to material type 1. Based on that you need to get this n value. Of course you can use it either way. You can convert whole to material type 1 or material type 2 or any other materials. Based on that you need to decide or you need to fix it this n value. Okay, now you can rearrange these things like this. Okay, and we can take the next one and convert. I'm actually converting whole to material type 1. I'm already explained. Oh, you can go either. Then better to use if you're going to convert whole to material number 2, then you better to go E1 divided by E2. Okay, E1 divided by E2 if you're going to convert whole to material number 2. Oh, in here I'm using material number 1, so that's why I'm using E2 divided by E1. Okay, now this is what you can see in here. So this dot actually represent y or y bar, sorry, y or y squared, any operation. Okay, so now think about these kind of arrangement. So you can see in here y squared in n, or y, where is y with n. Okay, any of these things going to represent by this dot. And dA, I'm working with dA now. dA means, think about this, I'm talking about like I'm going to convert whole thing to material type 1. So I'm going to consider this material 2. So material area 2 we're going to convert to material type 1 now in here. So in here, so I am going to create like a very small slip, very small slip in here in A time. So if the length is B, width is B, and this is a dy, it's very small area, so that's a dA. This is a dA. Now I am putting here to here, n to inside. In n is like some kind of value, so it's just scale value, so you don't need to, it's not a variable, so you can put it in without trouble. So now you have this one n time b. So what actually meaning, this is scaling of your width. So dy you can keep it. I'm giving different name to this one, b dash, that is a transverse section width. So now based on that you can transfer your whole section A2 to this way. So this is actually b dash. Similar fashion you can transfer here, of course 0 multiplied by n, just you need to multiply by n. The ratio you can transfer in here. As it is, we are not going to do the transformation. If you go either under other direction, if you are working with other direction, if you're going to convert all to 2, then of course it is, you need to convert this part. Okay, it should be going inside in quiescent because of E1 is lesser than E2, E2 is greater. Okay, there's a total area now for transverse section. Total area A1, I'm not going to transfer, A1 plus A2 dash. Okay, without trouble. And again keep in mind here we are going to transfer width, not in this direction, because this is a symmetric axis. So through the symmetric axis we don't need to change. Okay, so only things we are need to play with this width. Keep in mind that's also okay. We are actually considering the variation of sigma along this axis. Okay, that's the only thing. Okay, and now so you can transfer, and this is transfer area, and y2 equal to 0. This is from equation 6. Where's our equation 6? This one. So you can change this value to a to dash transfer section, and that means we can put all together. Now we have like a one type material. Okay, all are like a one type material. We can put all together, and we can end up with one equation and one component, a dash into y. Again, this is means similar to your simple bending formula. Here that means this is first moment of area, no, Q. That means it should be 0. That means your neutral axis should pass through the centroid of, here the most important thing, transfer section. Okay, here we are using transfer section, so you need to transfer the section based on your criteria. That means like it can be, you can transfer the material 1 or 2 or any other type of material. You need to transfer first, and after that you need to find the neutral axis of that transfer section. Okay, that's the most important in transfer section. Okay, that transfer section neutral axis. Okay, and you need to work with the transfer section neutral axis. So simply your neutral axis should pass through centroid of that transfer section. And after that, equation 7 we can rearrange again. Equation 7 means this one. Okay, we are converting now whole to one type of material type 1, and you will end up with this equation. We simply know this is what is this one is I, but it is for dash. It is a I for transfer section through the neutral axis. That neutral axis also you need to find from the transfer section. Okay, so simply you will end up with this equation. Okay, and now equation 9. From equation 9 you will end up with this one. So you can see, I M, same thing, you can convert it, and then you know this equation from previous, and just you need to substitute 1 over R to here, and here you can see this is going out, and you will end up with very straightforward. Of course, in general case, in normal case, it will end up with sigma over n over I into y. This is if you think about like if you have like a only steel, think about like a steel kind of homogeneous material, then this is a I through the neutral axis. In here we have like I dash, so that means you need to transfer section, you need to get the transfer section neutral axis, and after that you need to get I through that transfer section neutral axis for transfer sections. Okay, y of course again from the neutral axis, transfer neutral axis per distance. Okay, so this is a simple equation. This is for material 1. If you are working with like a material 2, just you can show you this is the ratio, n is coming here. So just what you need to do, you need to calculate sigma 1 at that point, and you need to multiply by n, the factor. Of course, in here where factor is greater than 1, that means you will end up with some value bigger than sigma 1. Okay, this is a way of calculation. You need to transfer whole the section to one section, and after that you can do your simple calculation. To check this one, I like to introduce very simple example. So this is our example. So find here, actually I'm asking find the maximum bending capacity that can carry by given composite section. This is our composite section. Here what we can see is steel, timber and steel connection, actually sandwich panel case. And here all dimension 9 millimeters. In here, of course, here again we not able to use directly simple bending formula, sigma over mi over y. So now what actually we need to do, first you need to transfer this one. When you're going to transfer, you can use steel or you can use timber. In here actually I am going to transfer to whole to steel section. So then based on that you need to define your N factor. So N is then equal E timber to E steel. So based on this one 1 to 20, of course it's given here, so you can use it directly 1 to 20, and of course here you can see it. Steel to timber is this way, we are using other way 1 to 20, and simply you need to multiply the width. In here 200 it into 1 to 200 into 200, no? Then it will go in out, it's equal 10. So that's the thickness in here. Okay, other parts we are not going to transfer same type material, we are going to convert to steel. If you're going to convert all to any other material, so of course then you need to change it all these things. Here I am keeping steel as it is, timber I am going to change to steel. Now this is my section. Now you can see very nice this I section. First of course you need to find the neutral axis. Here you don't need to worry, directly you can find the neutral axis. From here to here should be 150, no? Isn't it? Now the second you need to find I dash NA. So I'm not going to explain this one, so you can directly find I dash NA. I dash means a transfer section, second moment of inertia about NA, neutral axis. And if you know those things, other side straightforward. So here I keep in mind, I change all my material to steel, okay? So now if you're working with steel, we are not going to multiply anything, just we are using simple equation, only thing I dash should be there. And the maximum stress you know how to calculate. In here they are given that maximum, sorry, steel, it is a maximum bend in stress is 120, other one is 10 for timber. So we need to find the maximum moment capacity. So how to calculate that? Means we need to find M. We know this value, it is 120, careful about unit, and Y in here again you need to keep it in mind, we are going the maximum, so you need to find the maximum value. So that means I have I section, neutral axis, so the maximum you know we can get the top of the surface. That means 150 plus 10, no? 10 is 116. So based on that you can see if you are working steel, so it should be equal or lesser than 88.9 kilonewton per meter. Now we can work with the timber. When you come to timber, we convert this whole section to steel. So then if you work with timber, you need to put N front. So N is 1 over 20 and into this one 150. So you know in here, sorry, when you work the timber, careful, wait, in pencil, so this length 150, no? Maximum where we can see in here, okay? In this steel we can see here, okay? So that's a 150. So if you're using timber, the maximum value, this is 10, no? 10, 158. So but we know if you're using fully timber, this is the bending capacity. If you use steel, this is bending capacity. So but we have like a combined one, that means we have steel, wood and steel, okay? So to safe side you need to use the most smallest one. That means this is the value that we can use as a bending capacity of this cross section, and this is a usage of simple bending formula, M over I or Y with transfer sections. But think about if anyone like to use simple shear formula, then how are you going to use? Wait a minute, I will explain that one also in here, so then you can think. So I will take pen. So now think about anyone, our this section is like this now. Okay, so anyone, this is a steel and this is steel, this is timber. So of course there should be some connection, and if anyone like to work with that connection, then that person need to find the tau. So when you come to find the tau equation, you know tau equal SQ time I T. Okay, so this is if you have same material, but in here different material. So then you can prove the modified tau should be come with like a something like this. Of course, shear force not going to change. Q dash, you know now what is a dash means. I dash T actual. Okay, so you can prove it this one. You can check it with the internet or any other thing. You can prove similar way. So S is applied shear force. If you know the shear force is here, so straight, you are not going to scale in this one. Q dash means after transforming in this one, actually we transfer this one to this kind of arrangement. No? After our transformation, you need to find Q dash, that if you are interested about this layer, so then you need to come to transfer section and you need to work with this area. Okay, Q dash transfer first moment, and I dash again transfer section I dash. T is important thing that is not going to change. The transfer section, that means T is of course this length is not going to change. Okay, because of shear stress going to distribute about this axis, this is not going to change. Okay, T is real. This is transfer, this is transfer, this is real. That's only change. Of course, in the tutorial we have one question, so you can try by using this hint and you can get clear idea. Okay, this is the end of this lecture, and after that I will upload tube number 5. So I will show you till disregard tube number 5. This is your tutorial number 5. I will upload this one, so please go through this tube and try to study. Of course, these are straightforward thing. This actually cover about beam shear stress, and about build-up section. Okay, so there we can see 6 questions, and first 3 question work with shear stress, and last 3 question work with build-up connections. Okay, so please work with this one and I will upload, and after that we can shift to our next section about stress analysis of 2D plane stress problem. Until that, thank you.